The sun breathes. Not with lungs, not with the rise and fall of chest and ribs, but with something far more ancient and patient. From its corona, that ghostly atmosphere visible only during eclipses, streams of charged particles flow outward at speeds that would cross continents in heartbeats. This solar wind carries with it the sun's magnetic signature, invisible threads of force that stretch between planets like the finest silk woven from starlight and time. For 4.6 billion years, this wind has blown without pause. It has never known a moment's rest, never experienced the quiet of a still morning or the hush of evening calm. Scientists measure its velocity at roughly 400 kilometers per second on average, though during solar storms it can surge to twice that speed, racing through the vacuum at 800 kilometers per second. To put this in perspective, such particles could travel from New York to Los Angeles in roughly 5 seconds. Only took our star a few billion years to settle into this rhythm. The particles themselves appear deceptively simple, mostly protons and electrons, the basic building blocks of hydrogen torn apart by the sun's immense heat. Each cubic centimeter of space near Earth contains about 5 of these particles, a density so sparse it makes the best laboratory vacuum seem crowded by comparison. Yet, in their journey across the 150 million kilometers of space that separate Sun from Earth, they carry something profound information written in magnetic fields, a kind of cosmic script that tells the story of solar weather, of magnetic loops erupting from the sun's surface like slow-motion fountains of plasma, of the 11-year cycle that governs our star's mysterious moods. The solar wind emerges from coronal holes regions where the sun's magnetic field lines stretch out into space rather than looping back to the surface. Here, in these magnetic valleys, particles find their escape routes, following invisible highways that have existed since the sun first ignited its nuclear furnace. The process resembles water finding the path of least resistance down a mountainside, except the mountain is made of magnetic force, and the water consists of particles moving at nearly 1% the speed of light. Scientists still puzzle over exactly how the solar wind accelerates to such tremendous speeds. The corona, paradoxically, burns at temperatures exceeding 1 million degrees Celsius, roughly 300 times hotter than the sun's visible surface, a mystery that has persisted for decades despite our most sophisticated observations. The visible surface, the photosphere, maintains a relatively cool 5,500 degrees Celsius. Yet somehow, the corona above it blazes with incomprehensible heat. Somehow, magnetic waves and reconnection events conspire to fling these particles into the void, creating what astronomers call a supersonic flow that defies simple explanation. The sun's magnetic field itself wraps around our solar system in a vast spiral pattern, like the grooves on an enormous phonograph record rotating once every 27 days. This creates what scientists call the Parker spiral, named after physicist Eugene Parker, who first described how the sun's rotation stretches its magnetic field into elegant curves that sweep past each planet in turn. Only took humanity until 1958 to figure out why compass needles sometimes dance during auroras. Earth waits in this cosmic stream like a smooth stone in an eternal river, but it is far from defenseless. The planet possesses its own magnetic personality, a shield generated 2,900 kilometers beneath our feet in the liquid iron of its outer core. Here, in temperatures that match the sun's surface, iron flows in vast currents driven by the planet's rotation and the heat escaping from its solid inner core. These motions generate electric currents, and electric currents create magnetic fields, a planetary dynamo that has operated continuously for at least 3.4 billion years. This terrestrial magnetic field extends far into space, creating a bubble-like region called the magnetosphere that encompasses our planet like an invisible cocoon. On the day side, where it faces the incoming solar wind, this magnetic boundary compresses to roughly 60,000 kilometers from Earth's surface, about 10 times the planet's radius. On the night side, it stretches into a long tail that extends beyond the Moon's orbit, creating a magnetic wake like that behind a ship moving through water, except this wake extends for millions of kilometers through the vacuum of space. When solar wind meets terrestrial magnetosphere, the result is neither violent collision nor simple deflection, but something more elegant, a conversation between magnetic fields that speak the same fundamental language. The boundary where they meet, called the magnetopause, fluctuates like a living membrane, breathing in and out with the rhythm of solar wind pressure. During quiet periods, it expands outward. When solar storms arrive, it contracts inward, sometimes compressing to half its usual distance from Earth. This dialogue unfolds in slow time, measured not in seconds or minutes, but in the patient accumulation of magnetic pressure, in the gradual warping of field lines that curve and twist like invisible rivers of force, in the quiet dance of charged particles finding their way through corridors that exist only in the mathematics of electromagnetism. The process involves what physicists call magnetic reconnection moments, when magnetic field lines from the Sun and Earth touch, merge, and suddenly snap apart like rubber bands, releasing energy in brief, soundless explosions that illuminate the upper atmosphere. At the poles, where Earth's magnetic field lines funnel downward toward the surface, solar wind particles follow these invisible guides into the atmosphere, creating aurora sheets of light that ripple across the sky in colors determined by the gases they encounter. Oxygen glows green and red. Nitrogen burns blue and purple. These displays occur roughly 100 kilometers above the surface, in the thin air where the boundary between Earth and space becomes beautifully ambiguous. Only took evolution 4 billion years to produce observers capable of detecting this ancient exchange, to build instruments sensitive enough to measure magnetic fields weaker than those generated by refrigerator magnets, to recognize that the dancing lights in polar skies represent a conversation between our planet and our star that began long before the first cell divided, long before the first ocean formed, long before the solid ground beneath our feet had finished cooling from its molten birth. The solar wind carries with it the magnetic history of our Sun, evidence of storms that raged across its surface when Earth was young, records of magnetic cycles that have pulsed with clockwork regularity for billions of years. In this sense, every particle that streams past our planet is a messenger from the Sun's past, a carrier of information about nuclear fires that burned when the solar system was barely recognizable, when Jupiter and Saturn were still gathering the gas that would make them giants, when Earth was a molten ball, slowly learning how to breathe. Earth's invisible shield forms not in the atmosphere where clouds gather, not in the oceans where life will eventually stir, but deep within the planet's molten heart, where pressures exceed those found at the bottom of the deepest ocean trenches and temperatures rival the surface of the Sun. Here, 2,900 kilometers beneath the solid ground where future forests will root and cities will rise, liquid iron flows in currents vast and patient, driven by forces that dwarf hurricanes and monsoons, creating the magnetic field that will protect all future life from the solar radiation streaming endlessly through space. The outer core, a shell of molten iron and nickel roughly 200 to 300 kilometers thick, surrounds Earth's solid inner core like a metallic ocean that has never known the touch of wind or the pull of tides. Yet this iron sea moves with its own profound rhythms, stirred by the planet's rotation, by temperature differences between the scorching inner core and the relatively cooler mantle above, by chemical gradients that develop as lighter elements separate from heavier ones in the eternal darkness of Earth's interior. These motions, invisible and silent, generate electric currents measured in millions of amperes flows of charge that would power entire civilizations if they could somehow be tapped. Electric currents create magnetic fields. This fundamental principle of physics operates whether the current flows through a copper wire in a laboratory or through molten iron in a planetary core. But the scale here defies human comprehension. Currents that circle the globe, magnetic field lines that stretch from pole to pole, a dynamo mechanism that converts the kinetic energy of flowing metal into the electromagnetic force that shields Earth from cosmic radiation, only took the planet about 500 million years after its formation to establish this protective system. The process begins with convection, the same phenomenon that drives weather patterns in the atmosphere, but here played out in liquid iron at temperatures exceeding 4,000 degrees Celsius. Hot iron rises from near the inner core boundary, carrying heat toward the core mantle boundary 200-300 kilometers above. As it rises, it cools slightly and eventually sinks back down, creating convection cells that persist for millions of years. The Coriolis force, generated by Earth's rotation, deflects these rising and sinking currents, organizing them into helical patterns that spiral around the planet's axis like enormous metallic tornadoes moving through molten space. These helical flows stretch and twist magnetic field lines, amplifying them through a process scientists call the dynamo effect. Imagine holding both ends of a rubber band and twisting one end. The band becomes tighter, storing more energy. The geodynamo works similarly, except instead of rubber bands, it manipulates invisible lines of magnetic force, and instead of human hands providing the twist, planetary rotation and convective motion combine to strengthen and maintain the magnetic field. The mathematics describing this process fills textbooks, yet the essential mechanism remains elegantly simple. Moving metal creates magnetism, but the geodynamo possesses subtleties that continue to puzzle researchers. Computer simulations attempting to model core dynamics require some of the world's most powerful supercomputers, running for months to simulate what happens in Earth's core over mere centuries. The equations governing magnetohydrodynamics, the behavior of electrically conducting fluids in magnetic fields, exhibit chaotic properties that make long-term prediction nearly impossible. Small changes in initial conditions can lead to dramatically different outcomes. A sensitivity that helps explain why Earth's magnetic field varies in strength and direction over geological timescales. The magnetic field that emerges from these deep processes resembles, to a first approximation, the field that would be generated by a giant bar magnet tilted about 11 degrees from Earth's rotational axis. But this simple description masks extraordinary complexity. Superimposed on the main dipole field are smaller scale features, magnetic anomalies that reflect the chaotic nature of core convection. Regions where the field strength varies by factors of 2 or 3, areas where field lines emerge from the Earth at unusual angles. Paleomagnetic studies investigations of ancient magnetic fields preserved in rocks reveal that Earth's magnetic field has varied dramatically throughout geological history. Sometimes it strengthens to twice its current intensity, sometimes it weakens to mere fractions of its present strength. During the weakest periods, the magnetic poles wander across the planet's surface like lost travelers, sometimes moving thousands of kilometers in relatively brief geological intervals. Only took geophysicists until the 1960s to realize that continents drift and magnetic poles dance to similar rhythms of deep time. The field strength today measures roughly 25 to 65 microteslas at Earth's surface, about 100 times weaker than the magnetic field produced by a typical refrigerator magnet, yet strong enough to deflect the majority of charged particles streaming from the Sun. This seemingly modest field strength belies the immense energies involved in its generation. The total energy stored in Earth's magnetic field could power human civilization for hundreds of thousands of years, if only we could access it. Instead, it flows freely into space, creating the magnetosphere that extends far beyond the atmosphere, a magnetic bubble that encompasses the entire planet and reaches past the Moon's orbit. Scientists studying the geodynamo have identified several competing theories for exactly how Earth maintains its magnetic field. The prevailing model involves thermal convection driven by heat, escaping from the solid inner core as it slowly grows through crystallization of liquid iron. As iron atoms join the crystal lattice of the inner core, they release latent heat, creating temperature differences that drive convection in the outer core. This process also releases lighter elements that had been dissolved in the liquid iron, creating additional buoyancy forces that help sustain convective motion. Yet mysteries persist. Why did Mars lose its magnetic field while Earth retained it? Why does Venus, similar to Earth in size and composition, generate no detectable global magnetic field? How did Earth's magnetic field behave during the planet's earliest history? When the core was hotter and the inner core had not yet begun to crystallize, seismic studies suggest the solid inner core may have formed relatively recently in geological terms, perhaps within the last billion years, raising questions about how the geodynamo operated during Earth's first 3 billion years. The magnetic field lines themselves, invisible to direct observation, can be mapped using sensitive magnetometers carried by satellites orbiting hundreds of kilometers above Earth's surface. These field lines emerge from the southern hemisphere, curve through space in graceful arcs, and re-enter the Earth in the northern hemisphere, creating closed loops that guide charged particles along predictable paths. Near the equator, field lines stretch far into space. Near the poles, they dive steeply downward, creating the funnel-like geometry that will eventually channel aurora-producing particles into Earth's upper atmosphere. Deep in the outer core, where this magnetic architecture originates, iron continues its ancient circulation, indifferent to the life that will eventually flourish under its protection, unaware that its motion creates the invisible shield that makes complex chemistry possible on Earth's surface. The convection patterns that drive the geodynamo operate on timescales measured in thousands of years, while magnetic field reversals occur every few 100,000 years on average. Only took Earth's magnetic field 4 billion years to become essential for life, and life is still figuring out how to say thank you. The first magnetic storms arrive before Earth has learned to wear an atmosphere of oxygen, before the first cell has divided, before the planet's surface has cooled enough to hold liquid water for more than a few thousand years at a time. These storms are not weather in any sense that future meteorologists would recognize. No clouds gather, no winds blow, no rain falls. Instead, they represent the collision between two invisible forces, the strengthening solar wind carrying the sun's magnetic tantrums across space, and Earth's newly stabilized magnetosphere, that bubble of magnetic protection still learning its own geometry. When a coronal mass ejection erupts from the sun's surface, it hurls billions of tons of plasma into space at speeds exceeding normal solar wind velocities by factors of 2 or 3. These magnetic clouds, each one large enough to engulf several Earths, carry with them twisted bundles of magnetic field lines that originated in the sun's corona, frozen into the plasma like DNA strands carrying genetic information across interplanetary distances. The journey from Sun to Earth takes between 1 and 3 days, depending on the ejection's initial velocity and the density of the solar wind it encounters along the way. During the Hadean and early Archean eons, When Earth's magnetic field was perhaps half its current strength and still finding its equilibrium, these solar storms would compress the magnetosphere to unprecedented limits. The magnetopause, that flexible boundary where Earth's magnetic field meets the solar wind, would collapse inward to perhaps 30,000 kilometers from the planet's surface, less than half its quiet time distance. Imagine Earth's magnetic shield as a soap bubble being squeezed by invisible hands, deforming and flexing, but somehow maintaining its integrity against pressures that could strip away entire atmospheres. The compression triggers a cascade of electromagnetic processes that illuminate the upper atmosphere in colors no eye has yet evolved to perceive. Charged particles, accelerated by magnetic reconnection events at the magnetopause, follow field lines toward the polar regions like drops of water following grooves carved in stone. As they enter the thin atmosphere, roughly 100 kilometers above the surface, they collide with molecules of nitrogen, oxygen, and trace gases, transferring energy that causes these atmospheric constituents to glow with characteristic wavelengths of light. But the early Earth's atmosphere contains little free oxygen, perhaps 1 part in 10 million compared to today's 21%. Instead, the upper atmosphere consists primarily of nitrogen, carbon dioxide, water vapor, and trace amounts of methane and hydrogen. When solar wind particles strike these molecules, they create aurora displays dominated by the red light of excited nitrogen and the blue-green emissions of carbon dioxide, painting the sky in hues that would seem alien to future observers accustomed to the green and red aurora of an oxygen-rich world. These primordial aurora dance across skies that witness no sunset or sunrise in the modern sense, for the sun appears as a smaller, dimmer star than the one that will eventually power photosynthesis and warm the oceans where life will emerge. The young sun produces roughly 30% less energy than its mature counterpart, yet paradoxically generates more intense magnetic storms due to its higher rotation rate and more chaotic magnetic field structure. Solar storms that would be considered extraordinary in the modern era occur with routine frequency, sometimes lasting for weeks as successive coronal mass ejections follow one another across interplanetary space like waves in a cosmic ocean. The magnetic field lines themselves become visible during these intense storms, not through direct illumination, but through their effects on the aurora displays they guide. Curtains of light follow invisible magnetic highways from the magnetosphere's outer boundary to the polar atmosphere, creating patterns that reveal the three-dimensional structure of Earth's magnetic field. These aurora curtains can extend for thousands of kilometers across the sky, rippling and flowing as magnetic field lines stretch and snap back like rubber bands under the pressure of the solar wind. Scientists studying these ancient magnetic storms must rely on indirect evidence preserved in the oldest rocks on Earth. Magnetite crystals formed during the Archean Eon retain memory of the magnetic field, strength, and direction when they crystallized, providing snapshots of conditions billions of years ago. These paleomagnetic records suggest that early magnetic storms were indeed more intense than modern ones, capable of reversing the local magnetic field direction for hours or days at a time as particularly powerful solar events overwhelmed Earth's magnetic defenses. The storms also generate electric currents in Earth's upper atmosphere and on the planet's surface, creating what geophysicists call geomagnetically induced currents. These currents flow through any conducting material they encounter, the oceans that are just beginning to form, mineral deposits near the surface, even the molten rock that still comprises much of the early crust. In the modern world, such currents can disrupt power grids and communication systems. In the Hadean Earth, they simply add another source of energy to the complex chemical processes already reshaping the planet's surface. Only took the solar system about 100 million years to settle into the rhythm of magnetic storms and recoveries that would persist for billions of years. The Sun's magnetic activity follows an 11-year cycle that may have been shorter and more intense during its youth, creating a drumbeat of electromagnetic disturbances that early Earth learned to absorb and deflect. Between major storms, the magnetosphere slowly recovers its shape, expanding outward as solar wind pressure decreases, healing the magnetic wounds inflicted by coronal mass ejections through processes that operate automatically, without conscious guidance or external intervention. During the recovery periods, Earth's magnetic field exhibits a phenomenon that scientists call flux ropes, twisted bundles of magnetic field lines that store energy like coiled springs. When the next solar storm arrives, these flux ropes can uncoil suddenly, releasing their stored energy and triggering additional aurora displays hours or days after the initial impact. The timing of these delayed responses depends on the complex geometry of magnetic reconnection, on the angle between Earth's magnetic field and the magnetic field carried by the solar wind, on variables that modern supercomputers struggle to predict with complete accuracy. The early magnetic storms also begin shaping Earth's upper atmosphere in ways that will prove crucial for the eventual development of life. High-energy particles from the Sun drive chemical reactions that would not occur under normal conditions, creating trace amounts of complex molecules that rain down onto the planet's surface. Some of these molecules may serve as precursors to organic chemistry, though the details of this process remain speculative. Only took organic chemistry about 1 billion years to figure out how to make copies of itself. The aurora themselves persist for hours or sometimes days during the most intense magnetic storms, creating a nearly continuous display that bathes the planet in ethereal light. This illumination reflects off the surfaces of the first permanent bodies of liquid water shallow seas that form as the planet finally cools enough to prevent water from immediately boiling away. In these primordial pools, the dancing lights of aurora create patterns that shift and flow like living things, foreshadowing the actual life that will eventually emerge from similar chemical processes occurring in similar environments, under the protection of the same magnetic field that makes these aurora possible. The dynamo's quiet revolution unfolds in the planet's metallic heart with a patience that spans geological epochs, establishing patterns that will persist for billions of years while continents drift, supercontinents assemble and fragment, and life experiments with increasingly complex forms in the oceans above. Deep within Earth's outer core, where liquid iron flows at temperatures that exceed 4,000 degrees Celsius, convective currents organize themselves into a remarkably stable system, a planetary engine that converts the kinetic energy of flowing metal into the electromagnetic force that will shield all future evolution from cosmic radiation. The revolution is quiet in the sense that no sound can travel through the solid mantle that separates the core from Earth's surface. Yet the energies involved dwarf anything occurring in the atmosphere or oceans. Convection cells the size of continents rise and fall through the liquid iron, driven by temperature differences between the scorching inner core and the relatively cooler core mantle boundary 300 kilometers above. These cells persist for millions of years, slowly circulating molten metal through paths that spiral around Earth's rotation axis like enormous helical rivers flowing through three-dimensional space. The Coriolis force, that same deflecting influence that will eventually shape weather patterns and ocean currents on Earth's surface, organizes these convective motions into columns aligned roughly parallel to the planet's rotation axis. Each column extends through the entire thickness of the outer core, creating a structure that resembles a vast metallic forest where the trees are currents of flowing iron and the forest floor lies nearly 3,000 kilometers beneath the surface. These columnar flows stretch and amplify magnetic field lines through a process that operates according to the same physical principles governing dynamos in human-built generators, except scaled up to planetary dimensions and powered by the heat of Earth's formation and the ongoing crystallization of the solid inner core. The mathematics describing this geodynamo process involve equations that couple fluid dynamics, thermodynamics, and electromagnetism in ways that challenge even modern supercomputers. The Reynolds number, a dimensionless parameter that characterizes the turbulent nature of fluid flow, reaches values in Earth's core that exceed those found in any laboratory experiment by factors of millions. The magnetic Reynolds number, which describes how magnetic field lines become trapped and amplified in moving conductors, similarly reaches extreme values that place Earth's core dynamo in a regime where small changes can have enormous consequences. Yet somehow, despite this underlying chaos, the geodynamo stabilizes into a configuration that produces a remarkably steady magnetic field. The field resembles, to first approximation, that of a giant bar magnet tilted about 11 degrees from Earth's rotation axis, with field lines emerging from the southern magnetic pole, curving through space in graceful arcs, and re-entering the planet near the northern magnetic pole. This dipole field contains roughly 80% of the total magnetic energy, while the remaining 20% resides in smaller scale features that reflect the complex turbulence occurring in the outer core. Scientists studying the geodynamo have discovered that the system exhibits what they call dipole dominance, the tendency for the large-scale dipole field to suppress smaller-scale magnetic instabilities that might otherwise disrupt the dynamo process. This dominance emerges naturally from the geometry of core convection and the constraints imposed by Earth's rotation, creating a self-regulating mechanism that maintains magnetic field strength within a relatively narrow range over geological timescales. Only took the planet about 500 million years to achieve this stable configuration, roughly the same time required for the first oceans to form and persist. The inner core plays a crucial role in this stabilization process, even though it remains solid and cannot participate directly in the convective motions that generate the magnetic field. As the planet slowly cools over geological time, iron crystallizes onto the inner core boundary, releasing latent heat that drives thermal convection in the overlying liquid. This crystallization process also excludes lighter elements, primarily sulfur, oxygen, and silicon from the solid iron crystal lattice, creating compositional buoyancy that enhances convective motions in the outer core. Seismic studies suggest that Earth's solid inner core began forming relatively recently in the planet's history, perhaps within the last 1.5 billion years. Before the inner core existed, the geodynamo operated through thermal convection alone, driven by heat escaping from the core through the overlying mantle. The addition of compositional convection when the inner core began crystallizing may have strengthened and stabilized Earth's magnetic field, possibly explaining why complex multicellular life appeared around the same time the magnetic field became strong enough to provide more effective protection against harmful cosmic radiation. The transition from purely thermal to thermochemical convection represents one of the most significant changes in Earth's internal dynamics since the planet's formation. Computer simulations suggest that this transition initially caused the magnetic field to fluctuate dramatically, with field strength varying by factors of 10 and magnetic poles wandering across the planet's surface before settling into the more stable configuration observed today. Paleomagnetic records from rocks formed during this transition period show evidence of rapid changes in field direction and intensity, supporting the idea that Earth's magnetic field experienced a major reorganization when the inner core began to form. The dynamo process also exhibits long-term variations that operate on timescales ranging from decades to millions of years. Satellite measurements over the past few decades reveal that Earth's magnetic field is currently weakening at a rate of about 5% per century, while the magnetic poles drift across the planet's surface at speeds of tens of kilometers per year. These changes reflect ongoing adjustments in core convection patterns, as temperature and compositional gradients evolve in response to the planet's continued cooling and the growth of the inner core. Some of these variations may be cyclical, driven by interactions between different modes of convection in the outer core. The Atlantic and Pacific hemispheres appear to exhibit different magnetic field behaviors, with the field weakening more rapidly under the South Atlantic while strengthening slightly under the Pacific. This asymmetry may reflect the influence of lower mantle structure on core convection, as temperature variations at the core mantle boundary create preferred pathways for rising and sinking ion flows. The geodynamo's stability has profound implications for the development of life on Earth's surface. Without a strong magnetic field to deflect most cosmic radiation and solar wind particles, Earth's atmosphere would gradually be stripped away by solar heating and electromagnetic forces, following the same path taken by Mars after its magnetic field weakened and eventually disappeared. Venus, despite its similar size and composition to Earth, generates no global magnetic field and consequently possesses an atmosphere dominated by carbon dioxide at crushing pressures and temperatures exceeding 460 degrees Celsius. Only took evolution nearly 4 billion years to produce observers capable of recognizing that their planet's habitability depends on invisible processes occurring at depths greater than the distance from New York to Los Angeles. Processes that convert thermal energy into electromagnetic protection through mechanisms that operate according to physical laws discovered only within the past few centuries. The geodynamo continues its quiet revolution, indifferent to the life it protects, unaware that its magnetic field makes possible the complex chemistry occurring in Earth's biosphere. The same complex chemistry that eventually developed sufficient sophistication to study the planetary dynamo and marvel at its elegant operation. The convection patterns that sustain this magnetic field will persist for billions of years, gradually changing as Earth's interior cools and the inner core grows larger, but maintaining their essential function of converting planetary heat into electromagnetic force. In this sense, Earth's magnetic field represents one of the most successful experiments in planetary engineering, a system that has operated continuously for most of Earth's history, protecting an entire world and enabling the evolution of life forms complex enough to contemplate their own magnetic origins. Magnetic poles begin their wander across Earth's surface like slow travelers, following invisible paths through a landscape that exists only in the mathematics of electromagnetic force. Tracing routes that curve and meander according to the turbulent patterns of convection occurring thousands of kilometers beneath the solid ground. The North Magnetic Pole, that point where Earth's magnetic field lines dive vertically downward into the planet's interior, drifts across the Canadian Arctic at speeds that vary from a few kilometers per year to as much as 60 kilometers per year, depending on changes in the convection patterns driving the geodynamo deep within the outer core. This wandering represents one of the most visible manifestations of the dynamic processes occurring in Earth's liquid iron heart, a surface expression of the complex fluid motions that generate and maintain the planet's magnetic field. Unlike geographic poles, which mark the endpoints of Earth's rotation axis and remain fixed relative to the planet's surface features, magnetic poles move continuously in response to evolving patterns of core convection, following currents in molten iron that shift like weather systems made of metal flowing at temperatures exceeding those found on the Sun's surface. The North Magnetic Pole's journey can be traced through historical records of magnetic declination, the angle between magnetic north and true north measured by compass needles at various locations around the world. Early Arctic explorers, navigating by magnetic compass across landscapes where magnetic declination changes dramatically over short distances, unknowingly documented the pole's location through their navigation records. James Clark Ross first reached the North Magnetic Pole in 1831, finding it located on the Boothia Peninsula in what is now northern Canada, roughly 1,600 kilometers south of the geographic North Pole. Since that first direct measurement, the North Magnetic Pole has traveled more than 2,300 kilometers across the Canadian Arctic, following a northwest trajectory that carried it from the Boothia Peninsula through the Canadian Arctic archipelago and into the Arctic Ocean. Its speed has increased dramatically over the past several decades, accelerating from roughly 10 kilometers per year in the early 1900s to more than 50 kilometers per year by the early 21st century, a pace that, if sustained, would carry the pole from northern Canada to Siberia within a human lifetime. This acceleration reflects changes in the strength and geometry of convective flows in Earth's outer core, particularly in the region beneath northern Canada, where magnetic field lines associated with the North Magnetic Pole originate. Computer simulations of core dynamics suggest that the pole's rapid movement results from competing influences of different convection cells, with a strengthening cell beneath Siberia beginning to dominate over a weakening cell beneath Canada. Only took geophysicists until the 1990s to realize that magnetic pole motion could accelerate so dramatically within a human lifetime. The South Magnetic Pole exhibits its own independent wandering pattern, currently located off the coast of Antarctica in the Southern Ocean, roughly 2,800 kilometers from the geographic South Pole. Its motion follows a different trajectory than its northern counterpart, reflecting the asymmetric nature of convection in Earth's outer core and the influence of varying heat flow patterns at the core mantle boundary. While the North Magnetic Pole races towards Siberia, the South Magnetic Pole moves more slowly across the oceanic regions surrounding Antarctica, tracing loops and curves that sometimes reverse direction as competing convection cells wax and wane in intensity. The relationship between magnetic pole motion and core convection reveals itself most clearly in the mathematical models that describe how magnetic field lines emerge from Earth's interior. Each pole represents a point where the planet's magnetic field becomes vertical, diving straight down into the core or emerging straight up from it. The location of these points depends on the detailed three-dimensional structure of the magnetic field, which in turn reflects the complex geometry of convective flows in the liquid outer core. Small changes in convection patterns can cause magnetic field lines to tilt, shifting the locations where they become vertical and thus moving the magnetic poles across Earth's surface. Paleomagnetic studies of ancient rocks reveal that magnetic poles have wandered throughout Earth's history, sometimes following predictable paths, sometimes moving erratically as the geodynamo adjusts to changing conditions in the planet's interior. During periods of stable magnetic field configuration, pole motion tends to be relatively slow and steady. During times of magnetic instability, periods when the field strength weakens or when magnetic reversals approach pole motion can become rapid and chaotic, with poles sometimes moving thousands of kilometers in geologically brief intervals. The wandering poles create practical challenges for navigation systems that rely on magnetic compass readings. Airports must regularly update their runway numbering systems, which are based on magnetic headings, to account for changing magnetic declination as the magnetic poles drift. The magnetic declination at any given location changes continuously as the poles move, requiring periodic updates to nautical and aeronautical charts used for navigation. In regions near the magnetic poles, where magnetic declination changes most rapidly, These updates may be required annually or even more frequently. Scientists tracking pole motion use a global network of magnetic observatories, each equipped with sensitive magnetometers that continuously monitor the strength and direction of Earth's magnetic field. These observations, combined with magnetic field measurements from satellites orbiting hundreds of kilometers above Earth's surface, allow researchers to create detailed maps of how the magnetic field changes over time and to predict future pole positions with reasonable accuracy over periods of several years. The predictions become less reliable over longer timescales because magnetic pole motion depends on convection patterns in the outer core that exhibit chaotic behavior similar to weather systems in Earth's atmosphere. Just as meteorologists cannot predict specific weather conditions more than a week or two in advance, geophysicists cannot predict exactly where magnetic poles will be located decades in the future. They can, however, identify general trends and estimate the range of likely future positions based on current motion patterns and understanding of core dynamics. Magnetic pole wandering also affects the distribution of cosmic ray particles that manage to penetrate Earth's magnetic field and reach the upper atmosphere. These high-energy particles, mostly protons accelerated by supernova explosions in distant parts of the galaxy, follow magnetic field lines as they approach Earth, with most being deflected harmlessly into space. However, some particles reach the atmosphere near the magnetic poles, where field lines funnel downward into the planet's interior. As the magnetic poles move, they carry these cosmic ray entry points along with them, subtly altering the geographic distribution of cosmic ray bombardment over time scales of decades and centuries. The aurora zones, roughly circular regions centered on the magnetic poles where aurora displays occur, most frequently drift along with the poles themselves. Northern Canada, which experienced regular aurora displays when the magnetic pole was located nearby, now sees fewer aurora as the pole moves towards Siberia. Conversely, regions of Siberia that historically experienced fewer aurora now find themselves in the expanding northern aurora zone as the magnetic pole approaches their longitude. Only took the aurora a few decades to begin relocating from Canada toward Russia. This migration of aurora zones represents a visible reminder that Earth's magnetic field remains dynamic and evolving, shaped by processes occurring deep within the planet's interior that operate on timescales ranging from years to millions of years. The wandering magnetic poles serve as surface expressions of the geodynamo's continuing adjustment to changing conditions in the outer core. Ambassadors from the metallic depths carrying news of thermal and compositional currents that flow through liquid iron at pressures exceeding those found at the bottom of ocean trenches and temperatures that match the surface of the sun.